Hello. So good morning, everyone.
Good order.
And welcome to this session on green buildings with a special focus on low carbon and carbon negative concrete. So my name is Christian WURZER. I'm a researcher at the UKBRC Research Center and the CTO of NCHA. And I'm moderating this session today. A quick introduction. So we will have 5 presentations now, starting with Alejandro CASTILLA from ecoLocked, then Bryan from Glanris, Henrike RÖSE from CarStorCon Technologies in Germany, then Fabien MICHEL from VOLTIGITAL, and Simon STAUFER from Neustark. So I will give a short introduction before each presentation, and then we jump directly into it. Great, thank you very much, Alejandro. So we will directly jump into the second presentation, which will be from Bryan, the CEO of Glanris from the US. Bryan is a serial entrepreneur with several successful exits and now 4 years of experience in designing and operating biochar facilities and the development of specialized applications for biochar. He leads the development of Glanris biochar application development, including the patents on rice hull biochar in water filtration and work done in biochar and cement, inoculated soil amendments and tire production. With BET, a kiln producer, he helped design the rice hull kilns. So Bryan will talk about applications of biochar in concrete. So the floor is yours.
Thank you. All right, so my presentation is going to be a little technical. Apologize for that if some of you are looking for something at a higher level, but I'm happy to answer questions afterwards. Just to let you know, what I'm going to be presenting is the results from 2 universities in the United States, UC Davis, which is a major ag research university in California, and Colorado School of Mines, on the use of or analyzing how biochar can replace cement and go into concrete as an aggregate. These studies are coming out actually next month, and so this is a bit of a preview of stuff that's coming down the pike. So first off, a little bit about Glanris. We've been designing and operating a pyrolysis facility since 2019. We're a little bit different in that we came into this focused on building with a specific biomass, rice hulls, and looking to convert that, because of the high silica content, into a water filtration media. And so that's what most of our patents are on that we talk about here. It's on the water filtration product, because we're able to create dual functionality in that product that gives it not only the ability to remove organics the way an activated carbon does, but also to remove heavy metals, which is a key function of leveraging the silica in the rice hulls. So as we're going to be getting into in a bit here, a lot of what we've done is to work with major ag universities in the United States, looking at applications for this biochar, and not in the traditional applications in soil amendment, but what are the other things that we can be looking at? Because a lot of work has gone into already the analysis of how to put this into soil amendment products. And then lastly, when we got into this, we were very excited about leveraging existing technology, but had a hard time finding a kiln that could handle very lightweight material. Rice hulls are very light, and so a lot of the existing systems just didn't work that well for us. So we actually ended up partnering with a company called BET to customize a kiln, and we've now, I guess, sold about 15 of those in the United States. So it's actually up from the 12 that's on this slide. So it seems to be appreciated by others, and they're using it not just for for rice hulls, but for a number of other products. So a bit of a repeat of what Alejandro said already, but just to kind of hit it home, concrete is the most widely used substance on Earth after water, and it's growing at about 2.5% annually. So there's fairly wide disagreement about how much CO2 emissions are there. But if you look at the highs and the lows, it's between 5 and 9% of global emissions. The consensus seems to be closer to 8% if you're looking at where the bell curve is there. And just to compare that, aviation, which is an industry heavily dependent upon burning fossil fuels, is only 2% of global emissions. This is 4 times aviation. So, you know, if you really want to make a dent in addressing climate change and certainly CO2 sequestration, here's a great market to get into. So, and it's roughly, you know, about 1 ton of cement production is about 1 ton of CO2. And we'll talk a little bit more about where that is in a second. And again, back to Alejandro's point about we're building a Manhattan every month. There are around 4.25 billion tons of cement that have been produced already. And we have passed the point now where concrete outweighs the combined carbon mass of every tree, bush, and shrub on the planet. So, you know, that kind of gives you a scale of the concrete industry and the real need to address change there. So a little bit about concrete for those of you who don't know what concrete is. It's about 40, I'm just going to give high-level numbers here, about 41% gravel or coarse aggregate, large stones, about 26% sand or fine aggregates. Then you add water, about 10% Portland cement, and the rest of it is superplasticizers, the things that they add, and air to be able to address different climate changes, pourability, et cetera. But most of, between 70 and 90%, let's call it 80%, of the embodied carbon in concrete comes from cement. So if you want to address the problem of CO2 in concrete, the big elephant there is addressing the use of cement in concrete. So a little bit about rice hull biochar. In this picture in the background, you see what it looks like. Very fine granules, very friable, breaks apart easily. But it's about 45% carbon, about 45% ash, and most of the ash is this particular formula here of chemicals, which is actually very important in the development of concrete. We are IBI certified. We've got a hydrogen carbon ratio of about 0.35, so we meet all of the standards for being carbon negative. And our carbon credits, we've been in production, as I've said, for a while, so our carbon credits are up for sale on Puro. Just a little bit about what does it look like, because it's a little bit of a different biochar from other biochars. A lot of the pictures you'll see of other woody-based biochars look like a black sponge. This looks more like a corn cob. And you don't see a lot of porosity on here. And really what you're looking at there is the silicon carbon formations. And this is very important in terms of some of the properties that it adds for concrete. So as I mentioned, we've been doing a lot of testing with universities, specifically with the Colorado School of Mines, Lori Tunstall's research group there. They've spoken a lot about this. UC Davis out in Davis, California is a major ag research university in the United States. Mississippi State University. We've also worked with a group in the United States called Solid Carbon, who is on a similar mission to integrate biochar into carbon. And we've done a series of ASTM industry standard tests on mortar cubes. And this is really to look at mix variety and to test the durability or compression strength in the lab. So first thing I want to point out here is this is the compression strength here, how well the material stands up. And these are standard time periods that are used for cure rates. And they go on. There's a 90-day, there's a 6-month, there's a 1-year, there are multi-year tests that are done. And we're still doing some of those. This particular study, we came in, the rice hull analysis came in late in their overall biochar work. So by the time we were doing this, they hadn't gotten to, with one of the mixes, they hadn't gotten to the 56-day studies. But here what you're seeing is ordinary Portland cement in the red. After these time periods, you see what the compression strengths are. And then you see our material replacing 10% and 30% of the cement, and then a replacement of about 42% of the fine aggregates. So not replacing any of the cement, but just using it as a replacement for the aggregate. And what you can see is that, with the replacement of the cement, we're maintaining very similar compression strength early on, and then over time you see this builds tremendously, and at the 30% replacement of cement with our rice hull biochar, we're now up over double the compression strength. So this is really big news. There's a lot of the fear, obviously, in any structural concrete is the durability of the material over time, and particularly its ability to stand up to these kinds of compression strength requirements for structural building materials. So very, very exciting to see these kinds of numbers here. And again, back to what we were talking about with those numbers, and really just to highlight this one here, which had sort of the best effect, the 30% replacement of cement gave roughly a 70% reduction in CO2. Huge, huge numbers. And again, remember, cement's only about 10% of concrete. So 30% of the 10%, that's only 3% of the mix, gives you a 70% reduction overall in the carbon footprint. So very, very big numbers there. Oops, I need to go back. There we go. So this is another study. This is with UC Davis this time. This is one more time. There we go. This is the same compression strength. And then you'll see that the time periods are measured here in the different columns. UC Davis did not use any superplasticizers. We talked about that as a particular additive to help, so that they just wanted to go straight without any of the use of any particular superplasticizer. And here what you'll see is ordinary Portland cement. And these are at the 7-day, 28-day, and 90-day studies. You'll see what the compression strength is. And you'll see that our material performed about the same, and certainly was well above the guidelines. This green is the 90-day guideline, blue is the 28-day guideline, and the gray is the 7-day guideline. So we're well above these guidelines. And then what they also did, which is important, is compare it to other woody-based biochars. And here you see that they're significantly underperforming as a replacement for cement. This is not a measurement on their replacement in aggregates. This is purely a measure of their replacement of cement. And that's because they don't have the same, or typically the same pozzolanic material, or cementatious properties that rice hulls have. And that's really this next slide here. This is a measure of the pozzolanic reactivity. This basically what this is measuring is its cementatious, or its properties to bind the material. And what you're looking at here is various different materials. You've got quartz. This is coal fly ash. Coal fly ash is today one of the larger substitute materials for cement. But again, it's made from the residue of coal-fired power plants. So we need to be getting away from coal-fired power plants. So this material is actually going away. And a lot of people are asking, well, what can we replace that with? Well, here's the pozzolanic reactivity for rice hull biochar. And you'll see that we're pretty much the same, a little bit higher than them. And then compared to other woody-based biochars, you know, not even close in terms of its ability to bind. So, you know, reading from the reports that are about to come out on these two peer-reviewed studies, you know, what they found is that biochar, rice hull biochar, had the best results of any of the biochar tested. And just to kind of get into the why there, I mean, I can read that for you, or you can read it, but basically it's the silica reacts with the calcium hydroxide to form this, what they call CSH in cement terms, which is really the glue that binds everything together. And it had the highest scores of any of the materials that they tested. So very excited about these reports coming out and about this potential application. So, you know, happy to answer any questions. Give that back to you. There you are.
Thank you, Bryan. If there are any questions, we again have time for one or two of these. If you have any, just raise your hand and someone will come and bring you a microphone, I think. I hope. Yeah, there's one back there.
Hello, so Alexandre Lemevel, I work for Suez.
Can you speak up a little bit? I can't hear you.
Okay. Hello.
There you go.
So I'm Alexandre Lemevel. I work for Suez, and I'm wondering if you've tested, if we want to call it biochar, but from solid-derived fuel that may not have application in terms of ergonomy, but may have a solution into the concrete market. And yeah, I don't know.
I'm sorry. Can you repeat that question? One more time.
So I was wondering
Yeah.
if you've tested biochar from solid-derived fuel. So from, we call it CSR in French. It's much more like from municipal solid waste or other type of waste that we do a pre-treatment, then we do pyrolysis, and we get this biochar, this char, and we cannot use it in, sometimes we can't use it in, like to get back into the soil, but perhaps in concrete it might be a solution, and maybe this char is much cheaper, and maybe it's an opportunity, and I was wondering if you've tested char from the...
No, although I would say that there is a group in the United States that's looking at actually sewage sludge as a potential to go into concrete. Again, you know, what we were looking at is replacing the cement side of the equation. Most of the work that's being done with that material is on replacing the aggregate. Okay. And I think we're going to hear more about that in the next presentation. But what we've seen is that it certainly can work. I mean, we looked at that. And there you don't have to worry about the cementatious property of the material. So it's actually, in some ways, a bit easier to use if you can get it right. So I suspect that you probably can use that as an additive, replacing some of the fine aggregates in concrete.
Thank you.
Thank you. Good morning, everyone. Thank you so much for your presentation. My name is Philippe Boedek, and I work at Nereus Invest. My question, in terms of economics, you pay for the rice hull, and what is the cost of the production of the biochar from the rice hull?
Great question, because this is all about the economics. As Alejandro said, if you really want to make this scale, you have to be able to come in with very low green premium to the product. Cement today in the United States costs $150 a ton, which means that if you really want to be able to replace that, you have to come in at somewhere near $150 a ton. There certainly are people today willing to pay a little bit of a green premium. And again, remember, we're only talking about 3% of the overall mixture here. So, you can probably get away with a bit of a premium. So the work that we've been doing is around $200 a ton, which doesn't significantly affect the overall price of the concrete, but it's a little bit of a premium and the people that we've sold it to already. But, the question really is, well, what can you produce it for? Because if it costs you $400 a ton and you're selling it for $200, that's not a great business. So, and the answer to that really lies in scale, because, you said that you pay for the rice hulls. We actually don't pay for the rice hulls. There's not much of a market for rice hulls. And today, most of these hulls are either being, the rice producers pay to have them hauled away in the United States, or they're being burned, both of which they kind of want to get away from. So even with a very small incentive, $5 or $10 a ton, we could get all the rice hulls in the U.S., several million tons of rice hulls available every year. But it really gets down to scale. So to make this work, you've got to get, not in the pilot scale that we're at, doing 1,000 tons a year, but you've got to get to, 20,000 tons a year. At 20,000 tons a year, your production costs are, around $150 a ton. Well, that doesn't sound very exciting, except that we have 3 products that we sell in this. We sell electricity, we sell the carbon credits, and we sell the biochar. So if we can get our production costs down to around 150, and we're getting 150 for the carbon credits, and we're getting 150 for the biochar for the concrete, and we're getting roughly on a ton basis somewhere around $30 a ton in electricity from that, then there's a decent business that can be made there. Bit of a long answer, but okay.
So one more question, and quick question, quick answer, please.
Okay. Sorry.
Pascal Ronfard from Biochar FR. So I have one question on these impressive results that you show. Do you believe it's rather based on the pyrolysis technology that you use to make the biochar, or from the specificities of rice hulls as the biomass?
It's a bit of both, in that you've got to do it right, but really it's the rice hull properties that make the big difference, the silica in the rice hulls.
Okay, great. So we can directly jump into the next presentation. So thanks again, Bryan, for this presentation. We have a question and answer session afterwards as well. So our next presentation will be from Henrike RÖSE from CarStorCon Technologies in Germany. Henrike is taking care of press and marketing as well as international projects at CarStorCon. She has a background in technical marketing and project management, as well as product ownership for digital products and platforms in Germany and abroad. And the talk from Henrike will be about building the future, creating things in concrete and asphalt. And asphalt, sorry. So, floor is yours.
Thank you for that. So, I'm probably adding on a lot of what we've heard. I think it all goes really well together. You me? I have to eat the phone, good. So my name is Henrike, I'm from CarStorCon Technologies from Germany, and we create carbon sinks in concrete and asphalt with our aggregate ClimateAdd. And one point that has been mentioned, but I want to highlight, is the importance of biochar in industrial applications. Not only for the biochar industry itself to have broader ways for application and to have a higher impact of the industry, but also to highlight the co-benefits of biochar, because we create not only carbon sinks, but have multiple co-benefits that I'm going to talk about in the future. And I think we need those to push the industry and to reach that massive carbon sink and to make it an industry of scale. So I didn't pay attention which button to press. Is that one? The big one. Good. So ClimateAdd, that's our aggregate. And not only we can mitigate CO2 emissions, because we call it ClimateAdd as adding biochar, but also adding co-benefits to the material, but also to the industry itself. We can replace fossil materials, so not only as an aggregate, we also replace cement and fine aggregates. So we have an answer not only to the carbon sink, but also to resource depletion and resource scarcity in the construction industry. And we can show these enhanced material properties like the compressive strength, a water holding capacity, or better insulation effects in the final material. So all of that plus the carbon sink makes it for us one of those valuable applications for biochar. We can realize any kind of concrete application, though, as Alejandro mentioned, they need different, or they have different requirements. I'll show a few examples later, but one of the beautiful things is that we do not need any major changes in the existing processes. We can just use the processes as they are and add our material as an additive in the existing mixtures. Before I have a closer look into our technology, I do a little turn on pyrolysis on BCR in the CDR technology, but also construction industry. I've heard a little bit about that. I'm not going to repeat the Manhattan example. And I think you're all aware of pyrolysis. It's just a quick question, because we always go over that, but it's a conference that is so diverse. So if there's one who does not know the process and how it works, I'm happy to jump into that. Is there anyone who feels like I need to know more about pyrolysis itself? No, they all know. So I'm jumping over that. One thing I want to highlight on this slide is the synergy effects between the renewable energy plants, between a plant that is a technology that is existing. So we can create huge energies. It's a technology that is proven, other than other CDR technologies that need further investment or further technical research. It's a proven technology. The plants are out there, and we can create huge synergies within that existing industry. Also, there's no further infrastructure needed. So on one hand, we have this powerful new raw material coming out of the biochar, and on the other hand, we have this industry that is in urgent need of green solutions. An industry under pressure of the high volumes, as we heard the numbers, high emissions, and also raw material scarcity. There's this war on sand, and if we manage to replace not only cement but also fine aggregates, we have another answer to that industry. And I think this is one of the matches that we are trying to achieve with our material. So we have answers for that construction industry, not only the carbon sink, but the co-benefits. The durability that we mentioned in the carbon sink goes even further, because the biochar or the additive gets integrated in the material matrix, in the building mix, so it stays bond even after the life cycle of, or even after the end of life of the buildings, and even after recycling. So the durability is not only in the carbon sink, but even in the material further on. The emission reduction through cement that we talked about. And the creation of local value chains. I'm going to show that later in how we proceed, but really the creation of local value chains and local ecosystems, and the improved material properties that I mentioned before. The seamless integration in the processes is another benefit, as well as the stability of the material. Construction industry, they need this consistent, stable material. So that's one of the benefits also of the treatment that we offer with the biochar. So quickly on how the process looks like, we have the pyrolyzed plants. Again, as I said, local partners, like the idea is to have local biomass, local plants, local applications, so we can create those circles. And this also helps us as a company to scale and to build new partnerships wherever we source new projects. We treat the biochar, we create our climate art, and then we integrate that into various concrete applications. One thing about the local value chains, of course, is the lesser transport emissions, but I think that's a given. I brought an example. As I said, it's custom-based development, so the recipes vary depending on the local mixture, on the material, on the requirements. We have a few customers who shy away from replacing cement. We have others who say, how much can we replace? So depending on the application, we have different examples. I still felt I should bring a calculation just to demonstrate. This is an example for 1 cubic meter of concrete. And we also take into account the natural carbon sink. That's nothing we have to do anything with it. That's what the carbon does, or the concrete does by itself, but just to complete the calculation. We based this example on a SEM2. We have done SEM2, 1, 2, 3, also a thing that adds massively the recipe and massively the amount of the amount that we can enter into the matrix, but also the amount of CO2 we can save in the end. So in this calculation, the reduction of cement takes away 25 kilos of CO2. The carbon sink through the climate art material is another 154 kilos. And then the carbon sink is a bit lower than compared to the standard concrete because we have less cement in the mixture or in the recipe. So in that example, we can even achieve a climate positive concrete mixture, but as you see, or as I show in the few examples, we have all kinds. We have customers where we have just a reduction, so a bit greener concrete. We have climate neutral material, or in this case, even a climate positive. So I guess I jump into the examples. One that's our biggest project so far, and one I like because it is a house for new pyrolyzed plant. The customer produces biochar for agriculture applications. He needed a new home for his new pyrolyzed plant and facilities, and we built that out of climate concrete. It's our largest project so far. Built the pillars, the flooring, walls, ceiling, and a rough 3,000 cubic meters of concrete, of climate concrete, were produced, and we sequestered 260 ton of CO2 within that project. The next project, and that's one of the pioneers you were talking about. So we needed those pioneers to open the market and to start. But now the pioneers, they made other customers like technical railway companies to come and say, could we build or could we go into longer cooperations? Because I feel the pioneers, they proved that things were working, and now regular customers, public customers come and say, could we build on that? So this is one of the pioneers, and his vision is to have net zero residential and office buildings. So what he does, he works with wood, clay, hemp, lime, cork, water, CO2 reduced steel. So he tried to find that holistic approach for his family buildings. And also one thing that I have to say, but we liked it. He said, let's lower the amount of concrete needed. Let's take concrete only there where it is needed. And then take this concrete and make it climate concrete. So the possibility to be hybrid, to be integrated in other sustainability efforts, it's also a beauty from biochar. We don't say, oh, it's exclusively biochar, forget about all the other sustainability efforts. And this is one of the first projects we realized. I brought it here also to mention the hybrid approach. It's a family home in Austria. We built the basement, ceiling, walls, a carport, and the prefabricated stairs that you see on the right picture. But the rest of the building was realized with this classical Austrian wood shingle construction. To have another sustainability or another green building effect. And another larger project, wrong button. Another larger project is a project with a 2,200 cubic meters of climate concrete. And again, it's a factory hall for wood, gas, and a saw workshop. And we sequestered 100 tons of CO2 here. And I have one last example. It's a pilot project for an asphalt. So that, again, is a super interesting application we're looking in. We have built this, and we are currently developing further project, but it's more on the pilot side. The concrete side is already more developed. I think the pictures talk a little bit to themselves. Maybe one idea is the street that is renewed here is connected to the pyrolysis plant, to the for a local district heating network. So while connecting homes to the local district heating and to the pyrolysis plant, closing the street, we used biochar in the asphalt mixture. So again, to use this benefit. And I had a thought when we talked about communities earlier, maybe one idea is also to go there with all the offers that we have, to go there with the climate concrete, with the enhancement of soil and to make biochar itself a little bit more fancy among communities. So this is what we are. We do custom project development. We adapt the solution to the needs of you, of customers, of our clients. We are compatible with other sustainability solutions, and there is no process adaptation needed. And I think with that, I'm done. I might have time for questions. Thank you very much. And this is me.
Thank you very much, Henrike. So yeah, we have some time for questions. So there's one there. Do you have a microphone? Yes.
Thanks for the presentation. It's a bit new for us on asphalt. What is the typical rate is used as biochar?
For asphalt, I would not be able to tell. But I'm happy to explore. Again, that's in pilot, so for asphalt I couldn't say the rates. I'm sorry.
Any more questions? I saw another hand before, but same question? Okay. There was one.
It's probably more like a general question on carbon accounting to like both of you, because if I understood it right, in the US, also the carbon avoidance credits of the cement reduction can be claimed. Is that correct? Is the first part of the question. And then for maybe you, I also wanted to ask you the reduction in general that you show also with the carbonation, with the avoidance of concrete. Is that translating to carbon credits, or is that backed by like EPDs, LCA that then your client can claim? Just to understanding the environmental aspect. Thank you very much.
You want me to take the second part? Yeah, so coming back to the credits, again, that's also custom-based. We do have clients who want to use those credits as insetting. So they claim the credits, or we also are connected to Carbon Future for trading if they don't use them themselves. Didn't really answer your question. Good.
Yeah. So you asked about the carbon crediting for how we look at it. So we as a manufacturer of biochar, we get the credits for the production of the biochar, the sequestration of the carbon through the production of the biochar. There is also a methodology out there now that addresses the substitution of cement for other lower carbon products. And that's, as I said on there, it's about half a ton of CO2 per ton of substitution. So that's an emerging standard. I think it's only in US right now, but we'll see how that starts to expand around the world.
Okay, one last question.
What kind of biochar do you blend, please?
Absolutely, I forgot to mention. So we, thank you for the question. Based on woody biomasses, so we really have to chat a little bit because we also see the compressive strength on woody biomasses, and I'm super impressed by the results I saw from the rice hulls. But yeah, it works, and we see also the compressive strength improving.
Okay, thank you, Henrike, for your presentation. Now I follow up from what Henrike said, that we need probably more than one technology to solve our climate issues. So we are jumping a bit away from biochar now. Our next presentation will be from Fabien MICHEL from VOLTIGITAL, talking about concrete solutions for carbon removal and the circular economy.
Okay. Hi, everybody. So my presentation will be in French, but I can do that in English as well. I'm Fabien, founder of VOLTIGITAL, which is an engineering and consulting company in innovative low-carbon technologies. And we are now at the company creating a new one, which is CarboRock. And I will be presenting CarboRock today. So it's a solution for mineralization of CO2. So there is a little joke I think it works both in French and in English. So it's concrete solution for both carbon direct removal and also circular economy. One point I didn't mention is that we are based in Nantes also. So we are the local guys from the fair. So I think you all know this graph, so I will skip. One point which is maybe interesting to mention is that the road to the 10 gigaton goal, I mean, it's a very long road, okay? So we have up to 2050, but I think we're already late. So key point is that, okay, you know, les petits ruisseaux font les grandes rivières, so we need a lot of combined efforts to reach that goal, and it will not only one technology or one supplier. And probably with many more technology and many more suppliers, we're still short on solutions to match this target. Anyway, it should not be a reason to stop working on it. Our point of view at CarboRock is from the CO2 perspective, because we are more like process guys. And so the idea is that there are different sources of biogenic CO2. Biogenic CO2 is a very good proxy for atmospheric CO2, but with limited quantities, let's say. And we have also different use of CO2 that we can consider. So one question we have a lot is, okay, I can capture CO2 at my anaerobic digestion plant or in my factory. I have a biomass boiler. I may capture it. What can I do with that? And there are different kind of uses of the CO2, whether biogenic or not anyway, but only small part of these uses are considering the sequestration of the CO2. So of course there is a place for a lot of application of the CO2, but you can use CO2 for food industry, you can use the CO2 for industrial applications, you can use the CO2 for e-fuels, considering it, particularly if it's a biogenic CO2, it can make sense. But not all these applications can consider a good sequestration of the CO2. And CO2 is emitted anyway by all these processes. So it's a very interesting way to see, okay, you have biogenic CO2, let's take it and capture it into a process. So the process we are working on is not that simple mechanism, which is a reaction with calcium oxide to produce calcium carbonate. So it seems very simple, and we can also simplify this equation, but actually it's not what's really going on. It's much more than that. It's like if you take a combustion reaction, it could be very simple, okay, you take CH4 and then you have CO2 and H2O. But actually you have a lot of things going on. So what we can simplify here is that it's a reaction and diffusion mechanisms. And so you have some key aspect. I don't know if there is a pointer, but if you see this, like this sphere, okay, the CO2 will be attacking the material by the side, by the surface, and then you will have to go deeper and deeper to reach the feedstock for the reaction. And if you take too much time, or if you don't manage to go that fast into the core of the particle, then you may not reach 100% of the sequestration potential. So actually, if you take recycled concrete and you put it here on the ground and you wait 1 month, 1 year, 10 years, this concrete will get some CO2 from the atmosphere with very, very low concentration. So the reaction can be very simple. If you take one block, you will have mineralization just on the surface, so very small depth, but a surface. And the idea for us is to use this phenomenon to boost the capacity of storage of recycled concrete. So our purpose at CARBOROC is to work on concept of ecosystem of mineralizations. We have some CO2, different sources. We have some construction materials. Also sometimes it can be waste, but we will focus first on concrete, recycled concrete. So we want to take both into a proprietary technology reactor and produce two key things. One is recycled concrete, but carbonated one, and the other one is a certificate of sequestration. So let's say a CGR certificate if we are working with biogenic CO2. And then a good point with mineralization of CO2 is that we are not disturbing the current equilibrium. So the concrete waste go to a concrete waste deposit, which is either public road and not the road industry mainly, travaux publics en français. And we have also the recycled concrete that can be done either for ready mix or prefab concrete. The idea is that these flow, they already exist. So we just have to plug onto that and either carbonate the recycled concrete for the road or either for the concrete industry. So who we are? So we are a very young company. Actually, CARBOROC is not created yet, but VOLTIGITAL is also a young company. We're based in Nantes, and we have some pilot plants, very small one. I think these guys did a lot, much more. They did much more development in their companies. But okay, it's the third company I'm creating, so I used to be in a much larger one. I co-founded in 2008, so I know that it gets very interesting when you start producing and having references, etc. So here, CARBOROC is the first steps of the company. So we have 3 little projects. One is making samples in a lab. testing the condition of ideal carbon mineralization of the CO2. We have another project which is ongoing, which is a bench scale reactor, very small one, where we are testing different part of the technologies, the parameters for the carbonation, different kind of mix we want to use in the process. And we have a third project which is ongoing as well, which is to test the added value, added benefits of mineralization of CO2 for concrete materials. Obviously, if we store CO2 into the materials, we can improve the environmental impact of the concrete without touching to the cement, just working on the aggregates. But also, we can work on different parameters like reduction of the absorption or how to say that, having a better compressive strength impact and so on. But as you know, concrete industry, it's a lot of different ways to implement the product. So if you visit a mixing plant, ready mix, they may tell you they have more than 250 concrete that came out just from this plant. So actually, to be very efficient in that way, you need to test a lot for different applications because all customers, they have their different specificities. So we're working on this project with concrete suppliers, so we can ensure that our process match with their expectations, and each concrete manufacturer has its specifics for each of his project. So basically, we are a very young company, just starting, but we have already some project going on and some partnership. I will not mention a lot here, but if you want to discuss that, we can. So we have a booth at the CCUS pavilion, just in front. And last word, so we have some ambitions. There are few companies working on the CO2 mineralization, particularly in Europe. We want to be the specialist in France. Okay, that's an ambition. Maybe we manage that, maybe we won't. Obviously, there are other companies in Europe, more advanced, but maybe more specific on some topics. So, second point is that we do really think that mineralization is a key tool for decarbonation, and that it may not only apply to concrete waste, but there are a lot of different feedstocks, and also there are a lot of different CO2 sources. Obviously, CGR is great because you get paid much more for storing the CO2 in material, but still there are some other projects which are more like CCU with a much larger scale with other material, not construction waste, that could make a lot of sense, and we are really working in this area as well, so as mineralization technologies, not only on one product and one application. And also, our ambition is to contribute to this development because there are a lot of science-based solutions that are needed, and for this transition to a low-carbon world. And we're really thrilled to participate to that. So if you have some question, I think my presentation is already over. We can discuss that. Obviously, we did not say it a lot, but we can discuss more if you're interested by mineralization of CO2. Thank you.
Thank you very much, Fabien. If there are any questions, just raise your hand now. We have time for questions. Anyone? So I guess we skip the questions to see to go directly into the last presentation. So we actually are on time then. We have a question and answer session afterwards with all the speakers anyway. So our last presentation for this morning's session is from Simon Stauffer, Business Development Manager at Neustark from Switzerland. Simon is responsible for the development of CO2 sources as well as non-concrete storage projects at Neustark. With his many years of experience in plant engineering, he also provides support in the sales of storage facilities. Before joining Neustark, he spent several years in various management positions at Biochar in Switzerland, Spain, Germany and New Zealand. Before that, he spent 17 years at an SME for industrial drying equipment, 7 of them as the firm's CEO. He holds a diploma in mechanical and process engineering from ETH Zurich, as well as further education in business administration. So, the floor is yours.
Thank you. So, thank you for the introductions and for the speakers before, especially Fabien also. I can skip some parts of my explanations. Yeah, so I'm the last one standing between your lunch and presentation, so I will speed up a bit. So Neustark does CO2 storage in mineral waste and recycling streams. This is a permanent storage. We learned, especially in recycled concrete, CO2 reacts with the calcium hydroxide. Reaction happens in the pores, and we can store the CO2 through this mineralization permanently. We also treat other mineral wastes, for example, the incinerator bottom ashes or slags. In French, it's mâche from waste incineration, which can also mineralize, absorb significant amount of CO2. In average, we see in practice that with recycled concrete aggregates, we can store about 10 kilograms of CO2 in 1 ton of recycled concrete. With IBAs, so the bottom ashes, it's about twice or 3 times more, so 20 to 30 kilograms per ton in average. Always depending on the particle size and on the amount of cement in these aggregates or the amount of metal oxides. This mineralization, carbonization is actually a natural process. So each concrete wall absorbs a little bit of CO2 over the lifetime, and we just speed up and enhance it. One way because it's in particulates, so we have more surface for reaction, but mainly because we attack with 99% CO2 instead of the 0.04% we have in the ambient air. So with that we can do this process in a couple of hours. So already after 2 hours we have a saturation of about 70-80% of the potential. And a remark for these IBAs, another advantage besides CO2 storage is the better stabilization of pollutants in these IBAs, so mainly of heavy metals, because we fill up the pores with calcium carbonate, with limestone. These heavy metals are better bound in these aggregates and can better be used in concrete or in road construction. So about our business model or our CO2 storage value chain. We have the existing concrete or mineral waste recycling value chain. So concrete recyclers, which takes in demolished concrete, crushes it, sieves it out, sometimes washing, and then reusing it for new concrete as replacement for gravel and sand or for road construction. And we integrate our process without disturbing the material flow of this recycler. So a typical concrete recycler moves about 100,000 or up to 200,000 tons per year. So it's many, many tons, and each wheel loader we have to move that around costs a lot of money, so we want to avoid that. So our business model is that we actually sell a storage plant to the recycler. This storage plant, I will show later how that looks like. We source CO2, biogenic CO2, mainly from biomethane plants. we liquefy it, we transport it to the recycler, we sell him the CO2, we generate certificates, CDR, so carbon dioxide removal certificates, which we sell on the voluntary market to customers, so company with net zero ambitions, to compensate their non-reducible emissions. A part of this revenue we pay to the recycler as a storage fee in order that he can amortize, pay back his investment. So this is basically the business model we work with. There are some options, so sometimes the recycler wants to have some of these certificates retired and applied to his materials so that he can offer and sell CO2 reduced concrete or construction material. So this is how it looks like, demolished concrete, the upgrading, then on the other side the CO2 source with liquefaction, buffer tank, then transport mainly through isotainers to these storage sites. The reactor can be a silo, like in this example, existing silo, which we just make tight on the bottom and on the sides. In this case, we have retrofitted our injection system. You see also, there is somewhere a laser pointer, a buffer tank for CO2. So we want to have 2-3 days of independence from deliveries. We have an evaporator, a passive evaporator, to inject the CO2 in gaseous form in the bottom of the reactor. So we fill up the reactor from the bottom to the top. CO2 is heavier than air, and we measure the amount of CO2 going in, we measure leakage, and we measure the uptake potential of these specific aggregates in the reactor. There is other types of reactors, new silos. In this case, it's a silo, greenfield silo with 2 chambers. We have also semi-mobile plants, like in this case, which are filled up with a wheel loader. This is at the concrete recycling site of Holcim in Switzerland. They have several of these sites, and this equipment travels around, so every 2-3 months it's on another site to test their material, to mineralize all their recycled concrete aggregates. We have also developed a fully mobile solution, because some of these concrete recyclers, they work really mobile on the big deconstruction sites, and target is to integrate that also in crushing and sieving and reutilizing of these aggregates. So we have 2 of these machines just in fabrication, and they will be commissioned within the next months. Right now we have 13 storage plants in operation, so 12 in Switzerland, 1 in Germany near Berlin, and we have about 17 storage projects under construction, mainly in Germany, Austria, Switzerland. We have one first project in the UK, in London, and we start to work intensively also in France and in Benelux. So this is right now our market focus. For the CO2 sourcing, we have sources in Switzerland, in Germany. Under construction, we have 1 rather large in Austria and 3 in France. This is an example of such a concrete recycling plant with CO2 mineralization. That's the one in Berlin at Heim, so a bit east of Berlin. They treat about 200,000 tons of recycled concrete and mixed construction waste. That's why they don't reach the 10 kilograms in average, because the bricks don't react with the CO2, and as they have quite a significant amount of mixed construction waste, it's a bit lower. A similar project in Switzerland with a capacity of about 1,000 tons per year CO2 storage. This is a big industrial area which is taken down over the next 3 or 4 years, and after it's finished and all the concrete is mineralized, they will move this plant to another big deconstruction site. This is an example how the mobile plant can be integrated. Actually, it's a project we are in discussion in this region here, with a smaller amount, about 600 tons per year of CO2 storage potential. This is a CO2 source at the biomethane plant in Germany, in Dresden. In the foreground you see an isotainer as a buffer tank. Meanwhile there is a larger tank with 50 cubic meters storage capacity. Certainly biomethane plants are currently the low-hanging fruit for CO2 sourcing, because with the upgrading of the biogas into biomethane to inject it into the natural gas grid, they have to separate the CO2 anyway. So it's easy to capture, just have to be liquefied for storage and transport issues. Gray emissions for this liquefaction as well as transport we need to account, of course. For that, so for the electricity consumption, we have to consider the electricity mix of the country where the liquefaction is located in. That means France, Switzerland has quite a low carbon footprint, and with that we achieve a removal efficiency of about 93%. So that means from 1,000 kilograms of CO2 captured at the biomethane plant, we can sell certificates of about 930 kilograms. In Germany, with a higher electrical CO2 footprint, we are around 85%. We are certified by Gold Standard. This allows us to sell these certificates on the voluntary market, as I mentioned, to customers like banks, insurances, tech, IT companies. These are always long-term contracts over several years, 5, 10, even 15 years, for a certain amount of CDR tons per year. And this allows us to have also long-term contracts with the recyclers and with the CO2 sources. So typically we see contracts with 5 or 7 years with fixed conditions. Neustark itself, it's a startup. Now we call ourselves a scale-up from the Technical University of Zurich. Meanwhile, we are 55 employees, still growing. We have offices in Bern and Zurich, and since beginning of this year also in Cologne in Germany. We have several partnerships and research projects. One of these is also a geological storage in Iceland, with the target to get experience with CO2 logistics. Of course, it makes little sense to capture CO2 in Switzerland and ship it to Iceland to store it on the ground, but we already gained a lot of experience out of this whole logistics. Good, I think that's it. So one of the main reasons I joined Neustark 8 months ago was really the pragmatic approach. And this technology, it's not rocket science. It's technology which can be scaled up now. So we can have an impact now, we can scale up now. Our biggest competitor is time. And with that, I have finished. So if you have more questions, you can also visit us at our small booth at D28 with CO2 Value Europe. So thank you very much.
Thank you, Simon. If there are any questions for Simon specifically, just raise your hand. please. And the microphone will come to you from there. Otherwise, we have some time for a panel discussion now. If there's any interest before lunch, but I think we can open the floor in general. And my question was, because there are two different technologies that we saw now. So it's biochar and carbonization. And I was wondering, I wanted to start the discussion with asking what's the pain point for, so you're all a bit dependent on CO2 removal prices or revenues from that. And where do you want to see that this price to go to make you happy? To start to make you happy, maybe? Or just if you have any thoughts on that. Microphones are everywhere.
You meant for the CDR credits?
For the CDR credit, yes.
Yeah, so obviously there are two main conditions for these markets. First is volume, and second is price. With price expected to be as low as 150 euro or dollar per ton of CO2 sequestered. So obviously we have to work on that, knowing that there is a reduction curve on the costs. Let's say there are productivity gains, there are reduction cost of the capex and etc. But obviously some costs will remain the same. So if you have efficiencies, you have electricity costs that may or may not decrease, particularly in distributed areas. So at Carborock, we are actively working on how to reduce the cost, how to make projects that could work on EU ETS markets, much lower than the CDR. So EU ETS is today is 80 to 100. CDR is 400 to 500. So there is the CO2 doesn't know its color. So it's CO2. It's almost the same, whether it's biogenic or gray, fossil. But obviously the mechanism, the economic model will be very different. So we are working in the area, okay, let's have a much lower target so we can reduce the price, not now, but in very short time, and we have to do that with saving some parts of the process to be more effective in the years to come.
Yes, just you asked about pain points. This for us as a biochar producer, a little bit different for other folks, it's really about getting to scale. And all of this whole industry is about getting to scale, which means at scale you can produce at price points that are attractive for the industry. And we're starting to get there, but what's slowing it down are several things. Number one, financing for scale up of plants, particularly biochar, remains an issue, particularly in the United States. There's a bit of a catch-22 that goes on, that they want to see offtake agreements for all of the carbon credits, all of the biochar before they fund. And offtake agreements for the biochar is just not really a thing right now in the United States, unfortunately, although that's starting to change. But certainly getting to scale so that you can produce at price points that are attractive to the industry and don't carry a super green premium is an important thing. The other thing that's certainly that we're seeing with the people that we've been working with on the trials, and I was fascinated to see the examples that were shown here, it's hard to get permits to pour this kind of concrete in the United States. As a matter of fact, it's impossible. So to look at the scale of the projects that you guys were doing, that's not happening in the United States right now. And it's going to take a while to get there. What we're seeing is non-structural applications. So non-structural pads, concrete walkways, pavers, bricks. These are things that are starting to come online, but the volumes are very low. So, if the volumes are low, you can't get to the scale, and, so it's a bit of a chicken and egg. But ultimately what you've got to get to is you've got to get to scale, and you've got to get the funding to be able to get to scale. one of those things has to go first in order to be able to produce this engine which is going to drive CO2 down.
Yeah, maybe just quickly adding that, because I really like the idea of not being so dependent on the CDR pricing, but considering all the other the other aspects to the calculation, and also the still way too cheap price for the fossil raw materials that we're competing against. So there will be a change in the calculation the moment that like the scarcity goes even bigger of the raw materials, or the real CO2 price for the fossil materials, or they stop subsidizing. I think that's to take into account, and for sure to have a stable CO2 price or a CDR price would also help, but I think it's just part of the story.
Yes, so we have similar pain points. So one is on the regulation side for the reutilization of the recycled concrete aggregates, and we see many differences between the countries. So for example, in Switzerland, most of the recycled concrete is reused for new concrete and building construction anyway. In Germany, it's only a few percent, and the vast majority of the recycled concrete is just reused for road construction. And this has to do with regulations. In Switzerland, it's about the properties of the concrete. In Germany, it's about the mixture. And this makes it difficult for the constructors to use it. So this is indirectly for us a pain point. And the other one is permitting processes. So in some countries, that can take 6-8 months just to get a construction and an operation permit. And bottleneck are authorities, and this slows down the whole growth.
Maybe also then to add from the perspective of the BCR and biochar carbon removal. So I would say prices should be converging to these 250 euros per ton, or this is what is already foreseen as a path to enable the scale up of the industry. But this also comes together from the biochar production side whenever we are getting the most on the different sources of revenue. And this also involves including, for example, everything on the bioenergy side. So if a biochar producer is also not having these sources of income secured, this will make the entire business case complicated. And of course, you will always have from the buying side those Microsoft potentially trying to drop those prices, but I see that difficult for the industry, at least for biochar carbon removal, to scale at a lower price level.
Okay, thanks for that. Again, the floor is still open for questions, so raise your hand. Otherwise, I'll just continue. Yeah, there's one.
Thank you so much for all your presentation. Erwan from S3D Design Office. I would have a question for Neustark and CARStorCon. What's the minimum quality of CO2 do you need for your carbonation reactors? Another question would be, you both spoke about liquefaction plants, but would it be possible to use directly a CO2 pipeline directly from AD plant in order to use CO2 from the AD plant in order to decrease the impact of the process? Thank you so much.
Yeah. So thank you for that question or questions. So for the second one, yes, using the CO2 directly in gaseous form in a pipeline is the best case. And we have already such a project in Switzerland where the biomethane plant is only about 200 meters away from the concrete recycler. So this is paradise. We can skip the liquefaction, we can skip a lot of gray emissions for electricity and transport. But it really needs to be close, couple of 100 meters. And as soon as it's longer distance, we need to liquefy also to buffer and to transport. And quality of CO2 doesn't matter that much. So if it's liquefied, it has anyway 99%. And everything else we don't care. So we certainly don't need food grade CO2. It can be industrial grade or even worse. But with the normal upgrading and liquefaction process, we have enough high quality.
One question about the CO2 quality maybe is if you use biogas or you have to take care of the H2S, obviously. Normally it's done in the upgrading process. The H2S will be detrimental, but more for the mechanical of the reactor, not specifically for the process, but of course you have to avoid that. Also, one key question when using directly bio-CO2 is that you have methane, which is released anyway. So if you have membrane upgrading, it's small quantity, but the mineralization reactor will concentrate it. So even if it's vented today, when you get to concentrate that in a mineralization reactor and then release it, it might not be a good idea at the end of the day, even if it's the same quantities, but since when it's 0.7% released, it's not good. But if you have a much more quantity of release on one way from the reactor, we have to do something about that. Second point. And also, the mineralization process is a batch process, so you have a strong consumption at the beginning, and then it's rather flat. So you will have a different impact on the consumption. So you have to have a buffer anyway, or to lose some gas, which is also feasible because not all the gas requires to be valued, since today it's not valued. But if you consider that CO2 is a resource, bio-CO2 is a resource, and then you don't want to lose a part of it in the process of you have to do some, the piping is necessary, but you have also to manage the buffering because your consumption will be not straight as production of bio-CO2, which is rather straight. So you have to also handle that. In terms of energy cost, it's much better. In terms of integration, you need to work a little bit on that, of course.
Great, thank you. There's a follow-up question here.
Thanks for your presentation. First question for ecoLocked, sorry. If my understanding is okay, you told us 30 cubes concrete and you are able to add 6 tons of CO2, meaning 8% roughly. I take into account 2.4 tons per cubic meter for the concrete. It's definitely higher than the other process. Do you use liquefied CO2 or gas phase in your process?
Okay. So first, I would say the figures are right, but it's with biochar, right? So we are developing, let's say, these concrete admix products that are biochar based, and maybe just to answer that high climate impact that we achieve with, let's say, relatively low amounts of concrete, right? So those 30 cubic meters is because that first product is optimized for that high carbon sequestration. As Henrike mentioned, there are different types of biochar that have higher carbon content, wood chip, for example, so that allows us to sequester more without hindering those mechanical properties. And that is that first product that we developed, so optimized for climate impact. There might be other applications, right, where we can use other types of feedstocks and that are not necessarily targeted on climate impact, but on improving technical properties of the concrete.
Okay, thank you. Meaning nobody tries to inject directly CO2 liquefied in when you are producing concrete?
So people are doing that, but they are not on the panel today.
Okay.
just to add something also. In the mineralization of CO2 in concrete materials, we're working with past concrete blocks that are crushed. So these aggregates can be mineralized and then reused in concrete. And with adding the benefit, I mean, it's complementary solutions. Or used in road construction and pavement and so on. So it's two different mechanisms. Obviously, we are addressing the reduction of concrete of CO2 in the concrete at the end of the day with different approaches, different rates, but also different impact on sourcing and so on. So the two things can be combined somehow, since for the mineralization of CO2, we using the past cement that has been used before that.
Yes, to add that, you can inject a certain amount of CO2 in this fresh concrete or in the cement, but you will lose from the puzzolanic effect, so of the binding capacity of it. So that's why you can only do a very small amount. On the other hand, what we do have as a process is the mineralization of the residual waters in concrete mixing plants. So the water from cleaning the mixer and the lorries, the trucks, has some concrete in it, and we can carbonize that, mineralize to store also some CO2, and this water is then reused for the mixing of the fresh concrete again.
Great. So there's one more question in the front.
Thank you very much. Simon from Pyrogenesis. I might have missed earlier, but I did hear that there was a mention of 10 to 20 tons of CO2, or was it 10 to 20 kilos, sorry, of CO2 per ton of concrete using the, the kind of weathering process. However, with the biochar, Bryan, have you measured the uptake? And that's what I might have missed from your earlier presentation. Have you measured the uptake of CO2 per ton of the biochar enriched concrete that you're producing, please?
Yeah. So what we're doing, obviously, in replacing cement is looking at the CO2 sequestered in the rice hull biochar, and sort of to address the point that was talked about earlier about the scale of sequestration. Ours is a relatively low carbon content material in that we're only about half carbon and half silica, unlike some of the other biochars that are being used, the woody-based biochars, which might be 80 to 85% carbon. But for us, we're about 1.2 tons of CO2 sequestered per ton of cement. That's our ratio.
Let's say we focus more on how at least the concrete producers work on these figures in Europe. So on a cubic meter per concrete way, already more than 200 kg of CO2 that we are able to sequester.
Okay, so I think a last round of questions, just a brief mentioning of, we talked about pain points and also about the scaling issue, but what about the interest of companies you're working with? Do you see more interest from the construction industry for CDR solutions? Is that growing? Are they still hedging their bets, or what's your thoughts about that?
Yeah, obviously the construction industry, particularly in the concrete industry, they have a strong pressure to change anyway. So concrete is among the most used materials for construction, but it's not sustainable as it is today. So there are a lot of work, and they are looking in all directions to improve the CO2 content of concrete, because it's not possible to continue this way. So And even with the decarbonation of the cement plant, which is ongoing, so capturing the CO2 and sending it to the North Sea, for example, in Europe, it's not enough. So they have to move, and I think they're really looking in all the possibilities. So definitively we have a very, at least ours, but I think it's the same for all the participants. We have a very good interest from companies in the construction industry in order to reduce the CO2 content. But obviously, for practical reasons, down to earth, one of the main criteria is circular economy. Because if you talk about a good project on the CO2 base, but it does not ring a bell with the local municipalities, with the local people, okay, sending the CO2, capturing the CO2, sending it to North Sea, for example, could make a lot of sense on a CDR point of view. But for a local guy making local concrete in an average town in France, does not make any sense. But if you take, I take the CO2 from these plants and I will make a recycled concrete from this site work, and then I will make a new part of, how to say that, building blocks that can be used, people can see it every day, then it makes a lot of sense because it's circular. So this is also a good point we have. It's because it's circular economy, it talks to the people, and so they want to be part of it, even if they are just saving like 10 or 100 tons of CO2. They are understanding that they can see it, so it's real for them, and it helps a lot to develop solutions.
So a couple of points about the industry reaction. First of all, from the U.S. perspective, this is a heavily regulated industry. And so, you can't really get much done unless your solution fits into some existing permitted use of the material. And right now there is no allowable use for supplementary cementatious material, which is a category. Fly ash is in that. There are no allowable uses in the United States, okay? That doesn't mean it can't be used. It just means that you have to get exceptions to use that, which gets back to the permitting process, which is never an easy process. So it's slow, but the industry associations are looking at this. They're following very closely the studies that we participated in with UC Davis and Colorado School of Mines and others. University of Washington, I didn't talk about what they did, but their study, our material was also in that. Their study is now driving the city of Seattle, Washington, to adopt some low carbon concrete standards. You're seeing this also now start to happen in California. California has regulated that concrete by 2045 needs to be carbon neutral. Now, that's a ways off, and we keep kicking the can down the road and not addressing the problem. So, one of the things that we've done, obviously, is go back to the state of California and the trade associations in California that represent the cement industry and talk about, hey, here's a solution that doesn't affect the durability of your product, but can get you very close to your goals today. Because part of the reason that they're setting these goals out in 2045 is that they don't see a solution right now. And they also recognize that it's going to take time to get that into the normal process. But there are people out there today, and we've got a couple of these projects that are happening right now. Private individuals or companies that are concerned about the green nature of the projects that they're building. They're whether it's a concrete pad that they're pouring or a sidewalk or a building that they're doing, and are asking for lower concrete products. But to get that permitted requires some additional work. So in the United States, so I think we will get there, but unfortunately, it's going to take time to get that industry acceptance. Once that happens, And we're several years away from that happening in the United States, even to get into that category of supplemental cementatious material and match fly ash. Once you get there, then I think you're going to see a very rapid uptake of the material. Largely because there's one other factor that drives a lot of this from a construction standpoint, which is getting lead points for the environmental nature of your projects. For a lot of the municipal buildings and certainly large corporate headquarters, you can get lead points for the use of this material, and once they see that this material is accepted in the industry, I think that will drive a big uptick. And then once the future regulations kick in, and California is regulated, New York is now regulated, but they've all regulated 15 years out, you know, that it has to be at that nature. But once that happens, I think you may see people start to move those forward a bit, and I think you'll see adoption creep up.
Maybe just quickly adding on like a more you perspective, because we see the same thing. Like the industry is under pressure, and sometimes I have the impression that they just wait until the last second. They see the pressure, they start exploring opportunities, they start exploring solutions, they come, they want to learn, they speak to us, but somehow they still feel like this is going to pass. Like climate change is going to pass, they're not going to affect us. But then what we see is this EU effect, that the countries being so close together, like we have Netherlands with a strong regulation, we have Austria who says if your concrete has the same results, the same testing results as a standard concrete, you can use it. So all of a sudden there's a country very close to Germany who does things differently. So maybe that's just like wishful thinking, but that countries could affect each other with regulations and basically ping pong or have a snowball effect for better approach than the super strong regulations.
Also about the regulation, as committees that are editing the norms people there are people from the industry. It's a big name in cement, in concrete, and etc. So at least in France, so it's their interest, but it takes a slow time because they want not to be overwhelmed by new technology they cannot control. But at the same time, if they are too late, their industry compared to a steel industry or wood industry for the construction is taking a bigger part to the transition. So they have this double awkward role that they are the norm. They are editing them. They are making them evolve. So they want to slow down the process somehow, but they need to speed it somehow anyway. So at the end of the day, it can be solved like this.
Just maybe also to put some context on the power that each of the different entities can bring to the equation, and is that whenever you're faced with this process of certification for a building material, you have to go through a super exhaustive testing and proving that actually you meet the requirements. It should be on performance, as is in Austria, so actually that the concrete delivers. But at the moment, in many cases, it's just about the properties of those raw materials. And you could face a situation where you have to go through all of this, you have to invest $250,000, and then something might be wrong, and then you have to repeat. So for a startup, for example, like us, this could be the end, right? If we go to this path, we take this risk, and then things don't work out. And that's, again, my call to action for all those industry initiatives where we collectively develop this. Otherwise, for individuals, might be just really a very big burden.
Okay, so I'd like to call for collective action as the last words of the panel. And I guess I'll leave you all to waiting for 2 hours for the dinner now, lunch. So, have a nice day. And thanks to the panelists.